Today we'll be discussing how many of these are polar. We have 5 molecules, and we need to find if they're polar. So what we want to do is we want to draw the Lewis structure, identify bond dipoles using differences in electronegativity, and then to identify net molecular dipoles based on the molecular geometry. So first we have sulfate, SO3, and it has 24 valence electrons. So that Lewis structure will have sulfur in the middle with 3 oxygen atoms, and we'll connect these by a single bond and then finish the octets.
Dude, I have this ratchet pimple in my nutsack.
2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. But we need sulfate to have a full octet. So we're going to take away one of these bonds, one of these unpaired electrons, and have it as a bond. And this molecule will have resonance because 2 other Lewis structures could be drawn. Here, here, and here. And they're 3 equal domains. They're 3 equal domains because, which means it's nonpolar. Our second molecule
I think I forgot the white.
is O, oxygen difluorine. So it has 20 valence electrons with oxygen in the middle and then fluorine on each side, and we'll complete the octets. And if you count that up, we'll see that that is a full 20 valence electrons, 8, 8, and then 20. I was going to draw the molecular geometry here, which just kind of shows where the poles are. And then I'm going to draw the molecular geometry for oxygen difluoride, which will end up looking like this. And these poles go from oxygen to fluorine. Fluorine has the highest electronegativity on the periodic table. And these are going in the same direction, which will mean it'll have an overall pole going down, which just shows that that's polar. So now we come to barium dichloride. So we have BeCl2, has 16 valence electrons, and the Lewis structure looks like Cl, 6. And barium is one of the elements that can have a condensed octet, so it doesn't have to be filled. So barium does not have to be filled. And they both have even dipoles because it's the same element going both ways. So this molecule is not polar. Let me just go back and review. This molecule is polar, and this one up here, sulfate, is not polar. now we come to CCl4 carbon chloride, CCl4, I guess we can call it. Forgetting the name of it now, so it's CCl4. That has 32 valence electrons. So we'll have carbon in the middle and then Cl on the outside. And we'll fill all these octets. That's 8, that's 16, 24, 32. We have 32, so that's perfect. And each of the the bond dipoles all go outwards towards Cl. And if you look at the molecular geometry, it looks the same as the dot structure, which means that, actually I take that back, it's a tetrahedral. And it's non-polar because all the domains are pushing out evenly against each other, which it all cancels out. And then lastly, we have O3. And this has 18 valence electrons. So we have O, 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So we have 16, we have 18, so this oxygen will have a lone pair. But as you see, oxygen is a full octet, so we're going to have to take a pair from one of these and make it into a bond. And this structure will have resonance. So this bond will also flip over here and it'll take away this pair. So this structure will have resonance. Since there is a lone pair on the outside of on top of oxygen, the molecular geometry will be bent, and this will make the molecule polar. So I'm just going to go over the common mistakes that are made when calculating Lewis structures and valence electrons and whatnot. So you can draw the structure wrong, draw the molecular structure wrong, and that'll toss off if the molecule is going to be polar or not polar in regards to having a bond or an unpaired electron and just how they move the bonds. There's also counting the valence electrons wrong, which could just result in a wrong Lewis structure. Yeah, that's it. Thanks.